Imagine a perfectly organized system. It operates like a pristine library where every piece of information follows a strict, predictable pattern. You know exactly what to expect from every single row, until you encounter a sudden disruption, a data point that violates all the established rules of the environment around it. When you find a piece of information this abnormal, you face a dilemma. Is this a mistake that needs to be thrown in the trash, or is it the most important thing on the shelf? In data science, this disruptive element is called an outlier, and how an analyst handles it dictates whether a predictive model succeeds or fails catastrophically. To see this in action, look at this standard histogram. Standard data visualizations usually focus entirely on where the most typical values cluster together in the center. Because of that clustering, extreme anomalies can be almost invisible. The presence of a single extreme value stretches the axis so wide that the rare data points are too small to easily spot. But just because it is hard to see does not mean it is harmless. An unexamined outlier distorts the mathematical mean of a dataset, pulling the average artificially high or low. Watch the regression line on this scatter plot. A single rogue data point exerts so much mathematical gravity that it yanks the line of best fit completely off course. Unexamined outliers are mathematical threats. They skew means, warp predictive algorithms, and completely ruin the conclusions we draw from data. To protect the model, we have to isolate them. Because histograms are so good at hiding anomalies, statisticians rely on a visual tool specifically designed to drag them into the light. This is a boxplot, a visual shorthand built explicitly to diagnose how data is spread out. The central box identifies the interquartile range, or IQR. It safely contains the 25th to 75th percentiles, representing the undisputed normal data in your set. From there, the whiskers extend outward exactly 1.5 times the IQR distance. This sets an absolute mathematical boundary for expected variation. Any individual data point that lands beyond those whisker boundaries is officially flagged as an outlier. The boxplot has done its job. It doesn't tell us what to do with the anomaly, it simply isolates it so we are forced to interrogate it. For massive datasets, you use the programmatic twin of the boxplot, the z-score. On a normal distribution bell curve, a z-score measures exactly how many standard deviations a specific point falls away from the dataset's mean. In data science, any point that falls more than 3 standard deviations from the mean triggers an automatic red flag. Once that flag goes up, the most common amateur mistake is to immediately delete the row from the database. Take a dataset tracking the physical dimensions and places of diamonds. You might find a diamond listed as 0 millimeters wide, or a massive 59 millimeter diamond priced at only a few $100s. Basic physics and economics tell us these specific measurements are impossible. They are clearly data entry errors. But now, analyze a dataset of user purchasing habits. A z-score highlights a sudden, extreme spike in a customer's spending location and volume. This extreme spike represents a credit card fraud event, a vital signal that only exists because it broke the pattern. The math flags the point as unusual, but human context dictates its value. Professional triage requires you to always run your analysis twice, once with the outlier included and once without it. You have to measure its exact impact. If you confirm the anomaly is an error, like the 0 millimeter diamond, and it has minimal impact, do not drop the entire row. Dropping the row destroys perfectly good data sitting in the other columns. Instead, apply a surgical solution. Replace only the specific invalid value with a missing value indicator, like NA, and leave the rest of the observation intact. This precision protects the overall volume and integrity of your data, which leaves one final dilemma. What happens if an outlier massively changes your results, but you cannot definitively prove it is a mistake? Statistical integrity requires you to keep the data point if its origin remains uncertain. These rare events often contain the most critical information in a study. That massive deviation might be a critical structural engineering defect, a subtle cybersecurity breach, or a vital medical breakthrough. Stepping back into the library, we now have the tools to interrogate the single book that doesn't belong. But notice what is happening in the next aisle over. 2 entirely separate bookshelves are shifting and moving in perfect synchronized unison. What invisible mathematical force ties these 2 distinct sets of data together? We'll map that connection next time when we look at correlation.